Sinusoidal pulse width modulation is another technique of voltage control of an inverter. Instead of maintaining the width of all the pulses the same as in the case of multi-pulse modulation, the width of each pulse is varied in proportion to the amplitude of a sine wave. The distortion factor and the lower order harmonics are reduced significantly in this technique. Now we have a sinusoidal reference wave, triangular carrier wave in positive half cycle. When sinusoidal waveform is compared with the triangular waveform, then I'm going to get the gate signal G1, and in negative half cycle, this is my gate signal, and gate signal for Q4. Here we have a smaller one, and here we have a larger one. The gating signals are generated by comparing sinusoidal reference signal with a triangular carrier wave of the frequency Fc. So from here to here, it is carrier wave time period. In terms of frequency, this is 1 by Fc. This type of modulation is commonly used in industrial applications and abbreviated as SPWM. Now, the frequency of reference signal Fr determines the inverter output frequency F0, and its peak amplitude AR controls the modulation index M, and then in turns the RMS output voltage V0. The number of pulses per half cycle depends on the carrier frequency. Now, within the constraint that two transistors of the same arm cannot conduct at the same time, then the instantaneous output voltage will be, when Q1 is on, Q2 should not be kept on. This is the pulse in positive half cycle, and this is the pulses in negative half cycle. The firing angle for mth pulse is alpha m. The modulation index M equals to AR by this. This is our instantaneous output voltage. The same gating signals can be generated by using unidirectional triangular carrier wave as shown in this figure. Here the triangular wave is compared with the sinusoidal to get the output voltages. The RMS voltage can be varied by varying the modulation index M. It can be observed that the area of each pulse corresponds approximately to the area under the sine wave between the adjacent midpoint of half periods and the gating signals. If delta M is the width of the nth pulse, then the RMS output voltage V0 is given by Vs of sigma M1 to P delta M by pi under the square root. It will be equation 1. The equation of the coefficient of Bm from multiple pulse width modulation or uniform pulse width modulation can be written as Bn equals to sigma M1 to P 2 Vs by n pi sine n delta M divided by 2 of sine n of alpha M plus delta M by 2 minus sine n of pi plus alpha M plus delta M by 2 for n equals to 1, 3, 5 and so on. That is equation number 2. This equation we have written from the previous topic. The link is given in the below description. Please go through it. If you observe the harmonic profile for 5 pulses per half cycle, the distortion factor is significantly reduced compared to that of multiple pulse modulation. This type of modulation eliminates all the harmonics less than or equal to 2p minus 1. So for example, for p equals to 5, the lowest order harmonic is 9. The output voltage of an inverter contains harmonics. The PWM pushes the harmonics into high frequency range around the switching frequency of Fc and its multiples around the harmonics of MF, 2MF, 3MF and so on. The frequency at which the voltage harmonics occur can be related by f of n equals to j m f plus or minus k of Fc, where Fc is the carrier frequency, where the nth harmonic equals to kth sideband of jth times the frequency modulation ratio MF, which equals to 2jp plus or minus k for j equals to 1, 2, 3 and so on, and k equals to 1, 3, 5 and so on. The peak fundamental output voltage for pulse width modulation and sinusoidal pulse width modulation control can be found approximately Vm1 equals to dVs for d lies between 0 and 1. So for d equals to 1, this equation gives us the maximum peak amplitude of the fundamental output voltage, that is Vm1 max equals to Vs. But for single phase bridge inverter, V0 equals to sigma n135 to infinity 4Vs by n pi sine n omega t, from which Vm max should be 4Vs by pi, which equals to 1.278 Vs. This is for square wave output. In order to increase the fundamental output voltage, D must be increased beyond 1. The operation beyond D equals to 1 or greater than 1 is called over modulation. The value of D at which Vm1 max equals to 1.278 Vs is dependent on the number of pulses per half cycle, that is P, and is approximately 3 for P equal to 7. This is the graph between the peak fundamental output voltage versus the modulation index M, which you can see a linear change in between 0 and 1. Then when it goes to over modulation, then it is a non-linear. Now, over modulation basically leads to square wave operation and adds more harmonics as compared to the operation in linear range, that is D is less than 1. Over modulation is normally avoided in applications requiring low distortion. An example is uninterruptible power supply, that is UPSs, where the over modulation is avoided since it requires low distortion. This is regarding sinusoidal pulse width modulation, that is SPWM. If this video is useful, please like, share and subscribe.